to episode 5 about calibration factors, correction factors, equivalent factors. This is a very important concept and kind of the backbone of using light scattering devices, using photometers, using optical particle counters to take particle counts and light intensity readings and converting them to a pretty good estimate of the mass volume concentration of your dust. One thing I want to point out here is right now I'm using, and I have been using, PM2.5, PM10 dust monitors. The commercially available big boys that have been used typically in the market for occupational ways, the TSI dust track, the side pack, the Fisher PDR 1500, you are going to attach a size selector to them, like a cyclone, an impactor, and so you're only going to pass the residual size through the sensing volume and take a reading. I have found with these PM2.5, PM10 monitors, most of success, the best success using the PM10 level. And what it boils down to here is you see here's the PM2.5 fraction, here's the PM10, and your rest rule convention, because it's kind of wacky, you know, it's actually a PM4, but as you go up in particle size, you know, it sees a less and less percentage of those bigger particles, and as you get smaller, you get to see more and more of those particles. So you can see here, it's pretty much in between the PM10 and PM2.5. Here's your rest rule convention, here's your PM10, here's your PM2.5. And that's what I found is that I take my PM10 concentration estimate and I'm going to have to shrink it. My correction factor is going to be less than 1 to get it down to this respirable size. So I just wanted to illustrate that in general, if you're using a PM10 to convert to a respirable size fraction, that should be a higher number than what you end up with. That should be higher than the reference sample, the NIOSH 0600 respirable dust sample that you take. If it doesn't, if you have to take it times 2 or 3, if you have to take the PM10 concentration of the photometer times 2 or 3 or 4, that's a red flag. Okay, so there are many articles about correction factors, and I suggest you start with this one here. This is one of the first that I started with. Very good background on the science. Jeremy Slagley, he's got several good resources out there, but on the science of light scattering and this Lorenz-Mead calculations, this has a good explanation of correction factors, calibration factors. So I'm just going to read it here. When illuminated, a particle scatters light with varying intensity about the particle, with the intensity at any given angle based on the particle diameter and refractive index. A photodetector within a photometer measures over a certain narrow angle the total intensity of light scattered off the particles in the view volume of the sensor. The response of the photodetector is then correlated by a microprocessor to a measure of aerosol concentration, under the assumption that the aerosol measured has the same density, size distribution, and refractive index as the dust used to calibrate the instrument. And so the kind of natural knee-jerk reaction is, well, these photometers, they only measure dust. They can't tell you, you can't see your dust in particular. They count any dust, and that's absolutely true. The photometer will give an inaccurate indication of concentration for any dust with physical qualities that differ from those of the calibration dust. So the point here is that these are the things that cause differences: the density, the refractive index, and the size distribution. But this is one of the many good articles that you will find. Here's another one. This is a more recent one to get a look at. And so like they tested out these low cost monitors as opposed to the Slagley article that I showed you. They were looking at, I believe, the side pack. But they conclude for all PM monitors, the reference material used for the evaluation was the main contributing variable. And so that's where you're going to get your difference, is whatever dust the device was calibrated to, you're not going to probably have that same dust. So you're going to need to correct it. Now, to give you a little courage, I just wanted to share with you this. This was a response to the OSHA request for information on Table 1 of the OSHA Silica Construction Standard. This law firm, on behalf of a client, submitted this to OSHA, and they say, my client CIH has conducted side-by-side exposure determinations using portable instrumentation. Based on this work, it has been concluded that with proper operation and calibration based on the exact crystalline silica content of the dust, the particle counting electronic devices achieve comparable accuracy as the OSHA NIOSH Appendix A methodology. So this is good news. It's certainly possible that these photometers, you can get a good correction factor and use them for your dust. But I'll probably say this at the end of the video. You've got to understand that you've got to check out your own dust. That's the only way you're ever going to know, is to compare your own dust. All right, so here's a few other pointers I wanted to bring up. Okay, so density is a big differential, right? So in the Slagley article that I showed you, the first one, they were looking at corn dust, and the side pack instrument that they were using is calibrated to Arizona road dust. So the dust that it was calibrated to had a density of 2.77, the dust they were looking at. So assume everything else is the same. Assume you got the same diameter, the same refractive index, the same particle distribution. You're going to have a difference here in your mass volume report because your density is different. Now, the RASCAL monitors that I'm using use the OPC N3. I don't know if that's different than this N2 data, but the N2 uses a default particle density that's converted. When it's converted, it's 1.65 grams per centimeter cubed. Arizona road dust, which is commonly used, has a density between 2.5 and 2.7. That's commonly used to calibrate these instruments. But again, I'm using ambient air sensors, so the ambient air particles that they're interested in are probably going to be less dense than the silica particles, so it makes sense that its default density is less. So let's read this here. Therefore, the photometer will give a concentration value for any airborne dust measured as if it were the calibration dust. The most important of these physical qualities are density, particle density, refractive index, and particle size distribution. I'm going to show you a little thing on particle size distribution after I go through the correction factor. Now the good news is that apparently the majority of airborne particles have a refractive index of near 1.5. So according to the Slagley article, Arizona road dust has a refractive index of 1.5. Their corn dust had 1.53. Silica quartz apparently has 1.544. So that's not much of a concern. You can kind of scratch that off, your density and your particle size distribution. And of course, it's got to read the particle diameter pretty accurate too. So here's an example of the side-by-side. And I did this similar for the Synergist article. We had a mannequin, and we did the same exact thing, really. So here you have your TSI dust track. It's taking a reading right next to your NIOSH 0600 7500 lab sample. This is your aluminum cyclone sample. So this is what it is. It's side by side. You're going to compare your reading of your dust monitor. Here's the side pack with your reference, and that's going to guide you. That's going to recognize the difference in densities, for example. Okay, I wanted to quick show. So the Alpha Sense, this is another good article. This is the sensor that's in the RASCAL one. And so I'm going to talk about linear response. This is also very important. The mass concentrations from the optical particle counters, the OPC N3 alpha sense, in this case N2, were linear with those from the reference instruments for all aerosols, although the slope and intercept were different. Okay, so this is, you want linear. You don't necessarily, if you have a different slope, that means you've got to apply a correction factor. And there's something I wanted to show you here. Yeah, so this is an example of pretty linear. As your concentration goes up, your photometer reading changes in the same way. So you get a nice linear, as the concentration goes up, you get a nice, and the slope could be like this, could be like that, as long as it's linear, as long as it's straight. This is an example of not good. So you see here as the concentrations go up, it's not very linear. It's all over the place. All right, well, I hope you enjoy this next part here, which I think will bring it all home and should turn the light bulb on for you.
3, 2, 1. Contact is the secret, is the moment when everything happens. Contact is the answer, is the reason that everything happens. Contact. Let's make contact.
Okay, so the first thing I just want to show you as an example, so this is a PM2.5, PM10 monitor. It's a particle counter, so actually greater than 0.5, greater than 2.5 micrometer diameter particles. This is a particle count. Let me show you that again. PM2.5, PM10. Now watch it, it will tell you what these are. Greater than 0.5, greater than 2.5. So these photometers, they are counting particles, and how do they ascribe this mass volume concentration? This is 13 micrograms per meter cubed, this is 38 micrograms per meter cubed, PM10, PM2.5. Okay, so I'm going to attempt to explain that. Okay, imagine that this is your sensing volume. So I mentioned in the video before this, you know, to get a mass volume concentration, you need a volume. So imagine this is the sensing volume of the photometer. Now these PM2.5, PM10 are generally designed for ambient air. So let's say these are the particles that they are counting. And let's say there's 2 particles in this volume. So, and that's what I have here. So 2 balls. Now, how many micrograms per meter cubed does 2 balls give you? Well, that's where the density comes into. So they ascribe a certain density to it, and let's say it's 4. So this would be micrograms per meter cubed, and this is particle count. Now the particles I'm dealing with, silica, it might be counting the same size, the same general particle diameter, but golf balls being the same size as this golf ball, wiffle ball, but this is a lot more dense. So the trick is to, if I've got golf balls floating around my sensing area, but my photometer is going to report to me as if they're ping pong balls. So let's say in reality, when I have 2 golf balls, I have 6 micrograms per meter cubed in that sensing area instead of 4. So this is where your calibration factor comes in, and this is where you're side by side. So what you're going to do is you're going to do a lab sample, a NIOSH 0600, and you're going to get a respirable dust during the same sampling period. Now I recommend you go with a PPI impactor they're a lot easier to use. But regardless, so you take your reference sample, which is side by side, and it's going to weigh the particles in here. So it's going to tell you how much these two particles weigh. So when we talk about a linear reaction, well, let's say I add 2 more golf balls. So now I have 4. And now my reference sample is going to weigh this again. Now, if you wouldn't be weighing the water, you'd just be weighing the golf balls. So my photometer, if it's accurately counting these particles, if it's accurately seeing the size, it's going to report 12. So I've got 2 and 6, and now 4 and 12. So now I have the start of a linear, and this is the key. If my particle count goes up by a certain amount, my mass concentration, my mass volume concentration should go up. So that gives me a linear. So if I add 2 more ping pong balls here, it should be 8. And here we have a linear. Now in reality, the silica particles are not generally round, they're all jagged. So this is where some error comes in. You know, this is almost like aerodynamic diameter kind of thing, where you're estimating an equivalent particle count, but you don't really have to have an instrument that's calibrated, so to speak. As long as it is reporting some kind of using a density and it's reading linear, all you really need to know is what you're going to get from your reference sample. So again, your reference sample is going to tell you what your mass volume concentration is. And again, you would expect, if I were to do a side-by-side now, let's say I had a side-by-side with this kind of concentration, and let's say I add 2 more, as long as my reading goes up again in the same kind of linear response, all I need to do is apply that correction factor. So in this case, it's reporting 6 for 2 particles. Well, actually it's reporting 4 for 2 particles because it thinks I'm reading ping pong balls. So I have my, well, let's do 4. I have my 4 golf balls in here. Actually this is now 6, but imagine I have 4 in here. My monitor thinks I have ping pong balls, so it's giving me a reading of 8. But my actual reference sample, my side-by-sides, tells me it's 12. So that simply tells me that I need to take 12 divided by 8. Alright? 12 divided by 8 would be my correction factor. But, as I showed you in the video, in actuality, my PM10 level is going to be much more than my reference standard. So I find that my correction factor if it's reporting 10 micrograms per meter cubed, my PM10, alright, my reference sample will actually probably give me 3.5. Okay, so that would give me a correction factor of 0.35, and that's kind of what I find. Now the reason why it's more, even though it's golf balls, is because, as I showed you in the graph, the PM10 counts a lot more particles and my residual size is within there. But this is the concept of why the density, this is why you need a correction factor, because one of your main drivers is density. Now another driver is particle distribution. So I'm going to explain that. Very simple example here. Okay, let's say my dust that I create in the workplace let's consider it's a crate. Now the photometer is not going to see every dust or count every particle perfectly. But let's just say in my crate here I have 3 bananas, and I have 2 coconuts, and I have 1 watermelon. Okay? Now this is where your dust has to be consistent. If you have a consistent particle distribution, then this ratio isn't going to change. So let's say I have 6 bananas. So if this ratio stays the same, now I should have 4 coconuts and 2 watermelons. Okay? And let's say I've got 9 bananas. 1, 2, 3, 4, 5, 6, 7, 9. Okay? Now I'm going to have 6 coconuts, and I'm going to have 3 watermelon. So the key with particle distribution is, if I have a detector that can only see bananas, and I have to read these crates pass through the sensor and I don't know what's in them, but I can accurately see the bananas, well, as long as the ratio stays the same, I just need to scan how many bananas are in there. So if I see 3 bananas, I know the rest of the contents of the crate, so now I have my estimate. So particle distribution works the same kind of way. And this is what you're only going to find this out by testing it. You have to get multiple correction factors, and ideally what you want to do is you want to get data points as the concentration goes up. So as your reference concentration goes up, you want to have a spread, and you just want to see if you've got a linear response. That means that your slope is going to be a 1 digit. It's going to be 0.35 or 0.5, and it's going to be a linear response. But you need to make sure that it's reading, and you got to do it on different days. And if your correction factor lines up and is generally the same all the time, you know that you have a consistent dust, and you'll be able to predict a pretty good estimate. You'll be able to convert your PM10 to your RASCAL dust estimate.
You sure those tests were accurate?
Huh?
The tests, the one you made when you got here.
You mean the atmosphere test?
Yeah, is the air all right? I mean, can we breathe it?
Well, we are breathing it, aren't we?
Yeah, is it all right to breathe?
Yeah, sure.
You're positive?
Yeah, it's a little thin, but it's breathable. Why?
You sure you didn't make a mistake on those tests?
Hey, what's the matter with you?
I got a headache. I never had a headache in my life. I've got one now.
Maybe you got a fever.
I haven't got a fever. I've got a headache.
I don't know, Jack. The tests are all right. Matter of fact, I think I got the figures right here. Yeah, you see, the oxygen content is...
Look, I don't care about the figures. Why have I got a headache?
I don't know, Jack.
Well, something's giving me a headache.
I thought that's a pretty good snapshot, but I think I'm just going to have to plow through it here, because basically I have empirical evidence that gives me confidence that these photometers that I'm using are useful for RASCAL Silica compliance. So I'm going to show you the empirical part of it, and I wanted to further play this out because I got a little confused there because of the PM10 portion and the different densities and why my correction factor is less than 1. So I want to clarify that and just kind of spill the beans here. So as a reminder or an understanding, these are respirable silica particles. Okay, they're not round. This is what's floating in the air. And again, one of the benefits that I have in the construction work that I've done and in the stone shop is there's no competing dust. So that's very clear. If I try to take a side-by-side sample and I have this respirable silica dust floating in the air, and then I have, let's say, a wood dust or some other significant portion of some other chemical, that is going to mess up my correction factor. So whatever correction factor I get from that side by side, if the next reading I take, it's just the silica dust, okay, it's going to be inaccurate. So you have to have a controlled environment. This is for a consistent, and this is why I tried to explain the crates and the bananas and the watermelons and coconuts, because you have to have a consistent composition for your correction factor to be consistent. But anyways, so we do have these irregular shaped particles. Now they are still reflecting light. The sensor can still only see a certain size, and there is a detection efficiency. So each kind of size of particle, the sensor with lab testing and that sort of thing, you're not going to see 100% of every size bin, so that's another factor. But I just wanted to show you here. So these are, electron images of the actual nasty silica pieces. So that being said, I wanted to go back to this because this is where I got a little confused going through there. So again, the PM10 is theoretically reading all the particles in this portion here, this PM10 portion. And this is the residual portion. So when I have my lab sample, this is only the portion that lab sample is seeing. And so although my particles are heavier, my silica particles, my reference silica particles, although they're heavier, because I'm seeing more particles with the PM10 particle count than the residual sample, even though it's trained for particles that are probably less dense. And I showed you the alpha sense, the density, that's the default density. Even though it's ascribing lower density to these particles, it's still seeing more particles. And of course, it's a big difference when you get up to the PM10, these bigger sizes, way more. So the more you count these bigger sizes, even if it's a less dense factor that you're ascribing to it, I obviously am seeing a lot more dust and mass per volume concentration than the standard, than the reference. So that's why my correction factor is less than 1. Bottom line, the PM10 sensor is seeing more dust than what my residual dust reference standard. And that's, again, I think that's to be expected. So even though you've got golf balls here and ping pong balls here, it turns out that I've got to bring down the PM10 concentration, which again is, I think, intuitive. Okay, so I actually want to show you some results and what this looks like. So the first thing I'm going to do is I'm going to show you side by side, and this is the kind of environment that I've captured. Now this is with the Dialos photometer, which I showed you in the video. Okay, now this is a particular construction company, and you can see this was 2 days, 2 different days, and now this is different times in the day, but you can see my PM10 to residual dust correction factor was very consistent. So this is chipping of concrete in a construction environment. So you see here very consistent correction factor. So the composition of this dust is empirically, we're going to say, it's very similar. So I was getting a good match there. Okay, so this is an example of an environment. Let me get my laser pointer here. They're chipping. I got my side by side. And I just want to quick show you, give you an idea, because I just keep talking about side by side. But that's what that means. I've got the cyclone. This is the NIOSH 0600 sample, and here's my dust monitor side by side right there. So here's the air coming in. Here's the air coming in for the lab sample. And these are just the graphs that are generated, of course. So this is a time-weighted average. So I take the same time of my lab sample and my PM10 sample here, and I average my PM10. So I had a PM10 average of 1,304 micrograms per meter cubed, and my reference standard was 640. So again, I've got to adjust this down, and that makes sense. All right, and I'm just showing you here. So now when we move to a different kind of construction environment, different company, different tools. Now I'm also side by side here. So here's my PPI, here's the Dialos, here's the plant tower, by the way. And so what am I getting? Oh, I kind of went too fast there, but you see here, here's the dust. This is outside, and there's no competing dust really. All right, now we got inside, back inside. Now there is some competing dust here, which I'll briefly mention. All right, and here's inside again. Here's they were doing work in a room, and there you see my side by side. Now I'm going to mention this. One of the samples I took here, after they had done chipping, they were sweeping with a broom. And so they introduced, I think, a different composition, a different makeup of particles, and that's why this side-by-side sample is off compared to the others, and now I'll point that out in a second. Yeah, see, there's the sweeping. So now when I bring it into the stone industry, I'm still finding similar results, and I'm going to show you that. So again, here's side by side. We've got 3 different environments. So I've showed you traditional construction, track work, and now stone shop, and they're all related. Now, as I pointed out, for my Dialos samples in a construction environment, so this is not stone shop stuff, I think I clearly had a difference in indoor and outdoor. So, and this is what the correction factor is, this slope of this line of best fit. Okay, so here's my data points. Here's my PM10 compared to the side-by-side residual dust sample. And if you can draw a nice straight line as you go up in concentration. So my slope, that's my correction factor, 0.42. And for the indoor ones, 0.31. And so that's significant, and I think that has to do with indoors. You do have a little bit of competing dust. Here is my, I always include this, but this is the one where they were sweeping at the end there, and I think that threw off my data point. But here you have the indoors compared to the outdoors. All right. One of the nice things about making these videos is I can kind of clean up and get organized. And I'm kind of, I kind of left the construction stuff behind, and then I left the transit stuff behind, and now I'm just working on the stone shop. But I quick made these graphs to kind of put it all together. So this is all indoor side by sides, not in the stone shop. So this is construction at the transit and regular construction. And so our correction factor was 0.33 basically. Converting PM10 to residual dust, we got a very good correlation there, R squared. Now when you add the stone shop, which is all indoors, it pretty much stays the same. The correction factor is 0.32. Okay, so it went down slightly. Again, a very good correlation. If you just look at the stone shop, including the table milling, your correction factor was 0.31. But if you take out that table milling and you just look at these down here, so you see the correction factor is about 0.28. So it's really probably has its own correction factor at the end of the day, the stone shop, but it agrees favorably with the other ones. Not stone were 0.33, and the stone ones by themselves are 0.28. All right, so I hope that kind of gives you some idea here of how you can empirically over time with side-by-sides accumulation, you can end up with a pretty good correction factor that's going to give you a pretty good estimate. For the RASCAL, for the alpha sense, when I did a side-by-side, so these are the 5 alpha cents here in the stone shop. correction factors are very similar to each other. That's good, but look at that. They're very close to what I was getting with the Dialos. Now, one problem you're going to run into is sometimes when you do a side-by-side, you can't get a correction factor because your dust is so low. So my Respro dust NIOSH 0600 number for these two other samples here were too low. All I can say it was less than 1 and less than 0.69. And obviously you don't want to create a high dust environment just to get good correction factor data. So that's one of the things you might have trouble with is, you want a clean environment, but that can make it difficult to get a side-by-side correction factor. But this is the exciting part here, is a whole different sensor. Again, still a PM10, PM2.5, but I've so far gotten similar correction factors to the Dialos. Now to show you this, okay, let me go to an actual example here. So empirically, going back to the Dialos, we had this table milling event, which here you see the graph. It generates very high dust levels. Now the good news is there's no silica in this. This is a poured table. We make it ourselves. I took a bulk sample and the air samples of the person, and the side-by-side found no silica. So that's the good news. And it's a short duration, but it is very dusty. So here's my side-by-side with the beta. And so now I'm going to look at my correction factor for the beta. And this is also, this sheds a lot of light here. See how it's like peak, 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 peak? Well, this saw is moving back and forth, back and forth. This stays stationary except for it's attached to the saw. So when the saw moves, it kind of goes with it. But it's always at the same orientation. And so you can see here as the blade is moving, you're getting these peaks, which is can also shed some light. So, but very quickly here, I want to show you the empirical, what I would consider success. So my PM10 average was 9,283. I took that times the beta Dialos correction factor, and I estimated that the lab sample, the side-by-side, was going to come back 2,413 micrograms per meter cubed of Respro dust, or 2.413 milligrams per meter cubed. And it actually came back, the side-by-side, as 2,910. So not having any idea for this 80 minutes of sampling what the possible Respro dust concentration was during that sampling event. I think this is a pretty good guess, and this is evidence that the correction factor gave me a good estimate of Respro dust. So again, I predicted 2,413, and at the controls there is actually 2,910. So that's where you can get into the semi-quantitative part of this. All right, and I wanted to show you one more thing here. So, and this is why it's not perfect. This would be a good example of why you can't get a perfect reading. So here's the alpha sense, and it's being compared to a reference, this APS instrument. And so now you create an environment of 10 micrometer diameter round balls, a consistent reference environment. And you can see the alpha sense OPCs were actually reading it first. They oversized it. This is the counts, number per centimeter cubed, and you can see there's some instrument variability here with that. But the main point is that it actually detects particles in this size range. It kind of overestimates them. So this again might lead us to why our PM10 level is higher, even though it thinks the density is less, because it's even giving PM10 sizes more of a 12, maybe PM12, PM13 size. Now this is interesting because this is compared to the plant tower, and one thing they found is that the plant tower cannot see PM10 sized particles, whereas the optical particle counter alpha sense can. So that's why it's a superior sensor, I think, in this case, than the plant tower.